All right, we're recording. Now we will try to start. Well, before I share my screen and start the recording, we will introduce the first speaker, Haiying Shen from University of Virginia. And she has done lots of great work on clouds, and she also will do, her current talk is connected to a big emphasis at Virginia, namely the study of the epidemiology and things of the pandemic. So let's get started with that.
Thank you for the introduction, Jeffrey. Jeffrey, when you share screen, you choose the two options in the bottom.
Yeah, I've got those two options on the left chosen.
Thank
But
you.
I forgot to choose your application. Let's do that as well.
Good afternoon, everyone. My name is Haiying Shen. I'm an associate professor in the computer science department at the University of Virginia. I hope you are safe and healthy. Currently, we all hope that the COVID-19 pandemic can end as soon as possible. Distributed computing techniques can help us predict and prevent the spread of COVID-19. Today, I'm going to discuss the challenges of distributed computing for pandemic spread prediction based on large-scale human interaction data. As we know that pandemics such as COVID-19 poses a severe threat to public lives and economy. As of August 20th, 2021, there had been 209 million confirmed cases and 4.4 million deaths worldwide. The US economy alone suffers a total loss of 183 billion US dollars. Highly contagious virus such as coronavirus spreads rapidly among a large population. This figure shows the COVID-19 transmission on June 16th and on August 26th, 2021. We can see that the Delta variant of coronavirus spreads very fast during the 2 months. This figure shows the average daily cases per 100,000 people in different states in the US. Currently, nationwide, more than 100,000 patients are hospitalized with COVID-19. In this website, you can see 14-day forecast of the COVID-19 spread. Then, how can we do the forecasting for the COVID-19 spread? Computational epidemiology is a vital research tool for such forecasting and the designing of public health policy. It can provide insights on issues such as drug resistance, the rate of spread of infection, the epidemic trends, and the effects of interventions. Large-scale human mobility data plays an important role in the computational epidemiology. It can provide a more holistic view on the pandemic. It can help pinpoint the patient zero and better plan vaccination policy to achieve herd immunity. Also, it can help gauge the impact of preventive measures such as lockdown. Simulating epidemic on a very large population can be very computationally expensive. For example, the Biocomplexity Institute at the University of Virginia simulated the diffusion of coronavirus for the entire US people interaction graph, with 300 million people and 5.8 billion daily interactions for 250 days. This simulation can be completed within 24 hours. The epidemic simulation usually involves partitioning the graph to grids and performing the simulation on all the grids. There are three methods for the epidemic simulation. The first one is the SIR model. SIR stands for susceptible, infectious, recovered. The second method is actual pulp, and the third method is leopard. The goal of this work is to measure the performance of each of the three methods in epidemic simulation based on a large-scale human interaction data set, and identify the challenges in improving the computation efficiency and scalability, and also provide the research directions to deal with the challenges. First, let's see how each method works. SIR predicts the probability of being infected of each person or each grid's population. Usually, the SIR model is running in a single physical machine, so we call it a centralized SIR. In single machine, it performs all the necessary computations for the simulation. Since all computations are in one machine, it does not require the graph partitioning, repartitioning, data replication, or the communications between servers. The shortcoming of centralized SIR is low efficiency and low scalability for large-scale graph. The previous methods based on SIR are only focused on the prediction approaches, but do not consider underlying computing systems that support running the epidemic spread prediction jobs. Actual pulp uses a static partitioning approaches to partition the initial grid graph and uses the partitions throughout the entire simulation time period. Specifically, it uses the label propagation algorithm for the partitioning to assign an equal number of grids to each partition and also minimize the summation of the weights of the cut edges between the partitions. Then it assigns the partitions to physical machines or servers in a randomized manner. The connections between the partitions generate the communication bandwidth overhead between servers. For example, these two nodes are connected. Assuming these two partitions are assigned to these two servers, then this server needs to fetch data from that server, which generates communication bandwidth overhead and also delay due to data fetching. We can avoid such communications by replicating the data of this node into this server. In our experiment measurement, we added the initial replication into actual pulp to avoid the server communications. However, the human interaction data is time varying since people move around all the time. Therefore, the static partitioning is not suitable for time-varying graph. A partitioning result with few connections between certain partitions may not have few connections between those partitions next time. Then it will generate a high server communication bandwidth overhead. Leopard adaptively changes the partition assignment whenever there are changes in the grid graph. If the number of incoming or outgoing edges of a grid changes, Leopard assigns the grid to a low workload server that holds many neighbors of the grid in order to reduce the server communication. Leopard also utilizes replication strategy to reduce the communications between servers. In order to see the performance of the replication strategy, we also implemented Leopard without the replication strategy, denoted by Leopard RL. In our experiments, we used a data set that covers the entire state of Virginia from January 2020 to December 2020. The data set contains the unique IDs for individuals, their latitude and longitude coordinates, timestamps, and so on. The data acquisition frequency for individuals was varied from 5 minutes to 30 minutes. We thank Biocomplexity Institute at the University of Virginia for providing us this data set. We divided the whole state of Virginia to 10,000 grids. We conducted our experiments on Amazon EC2 instances and set the number of servers to 20 by default. The size of the infected population at a grid at the initial timestamp was set to 20%. These two figures show the completion time versus the timestamps and versus the number of servers respectively. The completion time is the total time required to complete the simulation. We see that the centralized SIR model generates significantly higher completion time than other methods. This is because it only uses one server, but other methods use multiple servers. The performance of other three methods follow this relationship. Leopard generates the lowest completion time, followed by Leopard RL and then extra pulp. Leopard can adapt to the time-varying graphs, but extra pulp cannot. It only uses static partitioning to partition the graph. Therefore, as a result, Leopard has 33% to 40% lower completion time than extra pulp due to its adaptive partitioning. Leopard has shorter completion time than Leopard RL because Leopard RL does not have replication, so it needs longer completion time. So we can see that the single machine approach performs poorly. Repartitioning and replication both reduce the final completion time, but they also generate their own time overhead. These figures show the time overhead for each operation, repartitioning, and replication versus the timestamps and versus the number of servers respectively. In the figure, the blank blocks with different patterns represent the computation time of different methods. The first bar is centralized SIR. The second bar is extra pulp. The third bar is Leopard, and the fourth bar is Leopard RL. The green part is for repartitioning time overhead, and the red part is for the replication time overhead. We see that extra pulp does not have the repartitioning for the time-varying graph. In Leopard, even though it has a certain time overhead for repartitioning, it reduces the total time overhead of extra pulp. In Leopard RL, there is no replication. Although Leopard has extra time overhead from replication, it reduces the total time overhead of Leopard RL. The experimental results show that the repartitioning time overhead is around 6% to 12% of the overall time overhead. The replication time overhead is around 7% to 18% of the overall time overhead. So the repartitioning and the replication reduce the overall time overhead or the completion time, but they also generate certain time overhead by themselves. Based on our observations from our experimental results, we identify challenges, possible solutions, and give research directions to deal with the challenges. So, what are important in improving the efficiency of epidemic simulation? Distributed computing is very important. Multiple servers running on partitions in parallel can speed up the computation. However, it also poses a challenge of reducing the server communication, especially for time-varying graphs. Therefore, the initial partitioning, replication, and repartitioning are important strategies to handle this challenge. Then another challenge is how we can reduce the time overhead of these strategies. Here are some research directions. For the repartitioning, only when the repartitioning time overhead does not overweigh the communication time overhead over a certain time period, then we conduct repartitioning. We can explore time-varying graph properties to devise computationally cheap repartitioning heuristics. For example, when a part of the graph is changing frequently, we do not need to conduct repartitioning. When a part changes to a state that will stay for a relatively longer time period, then we can conduct repartitioning. For replication, we need to avoid unnecessary replications that generate a high time overhead. Specifically, first, we perform the replication only for the grids that are assigned to new servers after repartitioning, instead of conducting the replication for all the grids. Conducting replication from the scratch on all the grids will generate a high time overhead. Second, only when a replication operation's benefit is higher than the operation time overhead for a certain time period, then we conduct the replication. If the interaction frequency between two people drops for a certain time period, the replication will not bring much benefit. All right, let me conclude my presentation. Large-scale human interaction data is important in epidemic simulation. In this work, we conducted a performance evaluation on the state-of-the-art methods based on large-scale and time-varying human interaction data in the Virginia state. Based on our experimental results, we provide future research directions for enhancing the efficiency and the scalability of the epidemic simulation over a large scale and time-varying graph data. Thank you so much. I will be very happy to take questions. In the future, if you have any questions, please feel free to write me emails. Thanks again.
Haiying, I have a question. This is Dennis. So I noticed that the of the algorithms, especially the good ones, of the from 4 servers to 20 servers, there was not a very big increase. Did you compute the actual speed up that you got or the computational efficiency?
Let me, Jeffrey, can I share my screen or not? Let me see if I can share screen. Jeffrey, can I share
Well,
screen?
I think you should be able to.
Yeah, yes. So that's a good question. Let's see. Yeah, so Dennis, you mean the improvement from 4 servers to 20 servers is not so significant, right?
Well, I can't tell actually.
Okay, yeah. So this is because this is too huge. The centralized SII is too huge. So if we, we remove this part, and then we can see the difference. So for example, you see this leopard actually has 33 to 40%. This is not for computation, it's for entire completion time, including everything. So if it's because of the scale, that's why the difference is not obvious here. And
yeah,
actually, you see this number, it's almost 40%.
No, I'm not comparing the individuals.
Oh, that's right. Yeah. So
I'm interested, in this speed up being going from 4 to 20.
It's not 5, is it?
Yes, it's not obvious, and that's a good question. I didn't look into the details. I thought that there is a decreased trend, but not so obvious. Yeah, this so I suppose, with 5 times more server, the entire compression time should be decreasing. So right now, I guess it might be because of this that's why it's not so obvious. After the meeting, let me take a close look at it. I will write your email, Dennis. I will figure out the actual improvement comparing the values.
The good news is that it doesn't get worse as you increase the number of servers.
Yes, right, exactly.
Yes,
and I would also say this.
Dennis, can I just make a comment, since I was going to ask exactly the same question, but Helen, do you think it could be due to the communication overhead? Since you mentioned the replication cost, and you didn't really say how much data is replicated every time at every time step, but if it is too much data being moved between nodes, that could explain.
Right. That could be a reason, and this is the time decomposition figure. So repartitioning takes around 6% to 12% of the entire time. Replication takes so much, 7% to 18%. That might be one of the reasons, and I need to take a close look at it. I'm not sure if it's
do you know the exact amount of data which is being replicated at each time step?
Right now, I don't know. So we set a threshold, and then when the communication frequency is higher than a certain frequency, we made a replica, and that threshold is referred to the previous paper. So right now, I don't have the exact number in my mind, and I will find it out and send it to you.
Okay, thank you. Dennis, sorry, back to you.
No, that's fine. I'm happy. So
I had a question. So if you think of this on a worldwide scale, some of the spreading is due to long distance interactions like airplanes and things, because those actually, I think, create the initial spread. Now, if you have these variable communication distances, that could produce some quite non-trivial load balancing challenges. And I wondered if you've got data sets where you could explore that.
Yeah, it's a good point. Actual pulp already tries to balance the load. So let me quickly go to actual pulp. So they try to assign, let me see, here, equal number of grids to each partition. And in the data set, I guess we don't have data from airplane because the data is collected from each individual's smartphone. And yes, so load balancing is important. And so POP already considered it. And yeah, so did I answer your question, Jeffrey?
Yes.
Yeah, and then we also needed to consider the heterogeneous capacities of servers. So right now, what I'm thinking is actually, we should not target to balance the number of grids. What we needed to achieve is the load will not exceed the capacity of server. Because the capacities, bandwidth, memory, CPU of different servers are heterogeneous. So if we just achieve the equal number of grids, and there might be a struggle, and so the servers cannot finish their parts at almost the same time, and then it will still delay the whole compression time.
Okay, so thank you very much. I think we move on to Tevfik now. Tevfik,
Okay.
do you want me to play the recording?
Sure, Jeffrey, yeah, you can play the recording.
All right, let's give that a try.
Good afternoon. I am Tevfik Kosar. I'm a professor of computer science and engineering at the University of Buffalo. Today, I'm going to talk about our Green Data Flow project, which aims to minimize the energy footprint of cloud and HPC data movement. So why is the reduction of energy footprint during data movement so important? According to data provided by Cisco, more than 1 zettabyte of data is moved over internet in a year. And the annual electricity consumed by the global data movement is estimated to be over 200 terawatt hours at the current rate, costing around 40 billion US dollars per year. Cloud and HPC data centers are responsible for most of these data movement, as well as the energy consumption. According to a survey done by Gartner Research among data center CIOs, around 60% of the participants identified excessive heat and insufficient power as the greatest problems they are facing in their data centers. Of course, there has been a lot of research in this area, mostly focusing on reducing the power consumption on networking devices, such as putting idle subcomponents to sleep, adapting the rate at which switches forward packets depending on the traffic, new architectures with programmable switches, switching layers that can incorporate different policies, and power-aware network protocols for energy efficiency in network routing. But most of the existing research is either on specialized hardware, which are very expensive to deploy at large scale, or unpractical in the short term, such as replacing the entire TCP stack, or they sacrifice from performance in order to achieve energy efficiency. In Green Data Flow, we propose an innovative application layer solution, which is low cost, very easy and practical to deploy, and does not penalize the performance while increasing energy efficiency. In most cases, the tuning results in increased performance as well as decreased energy footprint at the same time. This is achieved by application layer tuning of 5 system parameters we identified. These include the level of multithreading at the end systems, which we refer as concurrency, the number of TCP parallel streams created, the number of pending acknowledgements between file transfers, which is referred to as pipelining, the number of active CPU cores involved, and the level of CPU frequency scaling. According to our extensive studies in this area, these 5 parameters have been the most effective in both increasing the throughput as well as reducing the energy consumption if they are tuned together and wisely. Of course, these are all very well-known techniques for throughput improvement. What is not known is their impact on end-to-end power consumption and how to tune them together to achieve the best performance per unit energy consumed. And this is exactly what we do in Green Data Flow. Yes, there can be different trade-offs between energy consumption and performance for different use cases. We define this problem as a service level agreement-based optimization problem. In one use case, we minimize the energy consumption while providing a certain level of throughput guarantee. And in another use case, we maximize the achieved throughput given a certain level of energy constraint. This helps us to adapt and apply our models to a wide variety of application use cases. Our solution to this optimization problem consists of 6 steps. In step 1, we perform clustering to separate similar log entries, for example, similar transfers performed under different background traffic loads. The data transfer logs contain different parameters such as network characteristics, dataset characteristics, the tunable parameters that I have mentioned before, and the timestamp, of course. There is also a hidden parameter, which is the background traffic. The cluster sizes in the dataset are not uniform, and some parameters have precedence over others. That's why hierarchical agglomerative clustering is chosen as the most suitable choice for this work. We consider the hidden parameter, background traffic load, as another layer in hierarchical clustering. We make use of the temporal differences between logs as well as the inter-parameter gap and inter-throughput gap to cluster them accurately. For example, in this case, the temporal locality has higher precedence over other parameters. And in this case, interparameter gap has higher precedence. So the resulting clusters from this step give us the data transfer performed under similar network conditions. So this is very important to determine, since the offline optimization will depend on the real-time network conditions, and we need to identify that first. In the resulting graph, we have a data set clustered according to the external load similarity, as shown in this figure with different colors. The next step is to construct the surfaces representing the transfers performed under the same or similar external load. We observe bitonic sequence-like pattern over the data points. That's why we choose piecewise cubic spline to model the interpolated surface. Piecewise property provides enough flexibility to model while guaranteeing smoothness up to the second derivative to stitch those pieces. Then we calculate the Hessian metrics to obtain the local maximas on the constructed surfaces, as you see here. Now we have the optimal parameter combinations for different background traffics, but we don't know the external load for the current transfer we intend to perform it. So each surface is here, again, representing different background traffics based on historical logs. We have that information. The information that we don't have is to which of these surfaces the real-time background traffic corresponds. For this reason, we need to model the current external load. At any instance, the contending transfers are the known parameters happening in parallel with the user transfer. But there is also external load, which is not explicitly known to the user and not logged. We model the external load using the simple heuristic shown here. The next step is to map the current external load to one of the background traffic surfaces in the historical logs that we have created in the previous step. For this reason, we need to do sampling. And first need to decide the sampling region, since we want to minimize the amount of sampling we do. And not all regions in the interpolated surfaces would be interesting for sampling. As many segments contain suboptimal parameters, and some regions are confusing as they are too close to the other surfaces, such as here and here, for example. Sampling in those regions would not help us to choose appropriate surface, or they would increase the number of samplings that we would need. On the other side, the regions containing distinguishable characteristics of the surfaces and containing the local maxima of those surfaces are more compelling, such as here, as an example. And exploring those regions could lead to a near optimal solution much faster with minimal sampling. We are also interested in regions where surfaces are clearly distinguishable. The goal is to find the regions where surfaces are maximally distant from one another. This problem can be formulated as a max-min problem, as shown here. Selection can be done by taking the maximum of all pair shortest distance between the surfaces, and it will give us the regions where the sampling makes more sense, and also that would minimize the amount of sampling that would be needed. In the next step, we train our learning model. We use Levenberg-Marquardt optimization, which is a proven technique for solving nonlinear least squares problems. We reserve 70% of data for training and 30% for testing, and we perform 10-fold cross-validation for increased accuracy. The last step is dynamic tuning. Regardless of how well the offline optimization works, if the system cannot adapt well to the dynamically changing network conditions, it will not perform well. For this reason, we combine offline learning based on historical logs with dynamic online learning. During an active transfer, if the achieved throughput and energy consumption numbers are not within the expected range, this information is fed back to our model. And a new parameter combination is calculated, which is better capturing the real-time network conditions. This provides quick adaptation to the changing conditions and still satisfying the target SLA constraints. This work has a wide range of application areas. So far, we have applied it to 3 different use cases. The first use case is bulk data replication between cloud and HPC data centers, where petabytes of data is replicated overnight. The second use case is cloud-hosted web services, where millions of users can hit many small files from the same server at the same time. And the third use case is mobile IoT data transfers, where energy savings become especially crucial for devices that rely on battery power. For the sake of time, in this presentation, I will only report the results for our second use case, which is cloud-hosted web services. In our experiments, we used cloud nodes from AWS and Camelin Cloud in different parts of the world, as shown in this map. We had some nodes in US, some in Europe, and some in Australia. The network bandwidth ranged between 1 to 10 gigabit per second, and the round-trip time ranged between 40 to 240 milliseconds. The dataset consisted of files ranging from 50 kilobytes to 250 megabytes, representing text, image, and video files. In this specific experiment, we applied our optimization to the HTTP protocol. But in other experiments, we obtained similar results when the optimizations are applied to other protocols such as FTP, grid FTP, and SCP. And here's a glimpse to some of the experimental results we have obtained. We configured one of our SLA-based models to achieve minimum energy consumption and the other model to achieve the maximum transfer throughput. Our two models, min energy and max throughput, are shown on the rightmost of both graphs. We compared our models to standard HTTP clients as well as the state-of-the-art optimization models in this area. The results are quite impressive, as we show that we can achieve 48% less energy consumption compared to the best competitive model in this area, while achieving up to 80% higher transfer throughput. As accurate modeling for mixed data sets is more difficult, our improvement over other models when mixed data sets are used is much higher, as shown here. We also tested how our models perform when some throughput and energy constraints are imposed by the users. Some users may not want to go below a certain level of transfer throughput while minimizing the energy consumption. And some other users may not want to exceed a certain level of energy consumption while maximizing the achieved throughput. In this example given here, the users want to achieve at least 4 gigabit per second throughput, and here they want to achieve at least 6 gigabit per second achieved throughput. And the graph shows the achieved accuracy level by our model, which is shown with blue, and by the closest competitive model. Our experimental results show that we can achieve up to 60% higher SLA accuracy, meaning the achieved throughput being closer to the target set by the user, and up to 20% less energy consumption compared to the closest competitive model in this area. The results also show that if the target throughput set by the user is an achievable throughput for those network conditions, our models can perform with very high accuracy, 95% and higher, as shown here and here. Of course, in some cases, the target set by the users may not be an achievable throughput for those network conditions. On those cases, our models would fall short in reaching the SLA target, such as in this case, as expected. In summary, our Green Data Flow project provides an innovative solution to the energy efficient optimization of cloud and HPC data movement. The application layer solution provided by Green Data Flow is low cost, very easy and practical to deploy, and does not penalize the performance while increasing energy efficiency. We have tested and validated Green Data Flow models on different network settings with diverse datasets. We have observed that Green Data Flow can reduce the power consumption during data transfers considerably by up to 48%, while increasing the achieved throughput up to 80%. Considering the amount of data moved from and to cloud and HPC data centers, this work has a great potential to reduce the energy footprint at these centers, which is identified as one of the biggest problems by the data center operators. Finally, I would like to acknowledge that this work has been sponsored in part by NSF and IBM, and it has been done by the contributions of the members of the Data Intensive Distributed Computing Lab at the University of Buffalo. I will stop here and take any questions that you may have. Thank you for listening.
Thank you. Questions? So I had a question. So there was some work I studied once recently by ESNet, which teaches a deep learning network to essentially optimize network transmission. Have you looked at those methods?
I think I haven't seen that, Jeffrey, but so there has been quite a few work which looks at optimizing the data transfer performance using deep learning, machine learning approaches. So the major difference of this work from the other work is we don't only look at performance improvement, but also resource consumption. While improving the performance, and also trying to minimize the resource consumption while improving the performance. That's the most important difference from this work from the other work in this area.
Yeah, I saw that was a great thing to look at, but of course we can change the loss function in deep learning and include minimum energy as part of that loss function. And so it might be interesting to look at that, because we were looking at transmission across between CERN and the labs in the US for the LHC experiments. Okay, are there any other questions? Haiying, you're muted.
Hey, this is Haiying, Tevfik. So if there's any overhead in order to minimize the energy consumption?
That's a very good question, Haiying. So of course, applying all of these clustering, machine learning, and different techniques, it has some overhead, but that's a one-time overhead. So basically, training the model takes some overhead, and this is of course done offline, not during the actual data transfer.
Right.
But once the model is trained, the actual real-time overhead of applying the model is basically minimal.
Okay. Okay. Very negligible.
Yes.
Okay. Thank you.
Sure. Any other questions?
All right, let's move on. Thank you very much.
Thank you all for listening. Thanks.
Now we move on to Shantenu. Do you want me to play the video for you?
Yes, please.
All right, we'll do it.
Hello, everybody. I'm pleased to speak today about Impeccable, a pipeline for high-throughput virtual screening. In particular, this is work done in the context of COVID. This is work done across many DOE national labs, Brookhaven, Argonne, Oak Ridge, but also many universities, as well as many countries, including Britain and Germany. I have the honor of representing a very large team, which I'll discuss and present at the very end. So let's step back and try to understand what the specific context for high throughput computing in clouds and supercomputers is all about. Drug discovery is a very complex and very expensive and time-consuming process. I think we know all of that. Typically, it takes about 10 years and $1 billion to discover a drug through both computational and experimental means. This is clearly a very large both cost as well as time duration, which is arguably unacceptable in the best of times, but in times of COVID or a pandemic, it's simply not an option. And underlying all of this cost and time is the fact that it remains, the drug discovery process remains a very large space of possibilities. The number of 10 to the power 68 is often proffered as a possible number of compounds that have to be worked through. And clearly an exhaustive search is not an option. So over the years, what has become acceptable and known as an approach is a multi-stage pipeline, where you have at the very start cheap and cheerful, but also slightly inaccurate, less precise methods. And at the very bottom end, you have computationally expensive methods, but also much more accurate, much more precise. To the extent that in the industry, the last stage, which we'll talk about, is often binding free energy calculation. These can be gold standards of indicators of which drug candidate might be pertinent for the particular drug, namely binding of a drug candidate to a protein, often also called as a target. Now, this combination is important because no one method in of itself will have both the accuracy and the computational cost to identify a possible drug candidate, but combined, when we look at multiple stages and create a filtering ratio, we might be able to create the right, if you will, a sweet spot balance between accuracy and cost to try to advance a large number of drug candidates through and promoting only those that are promising at each stage until we're left with a very few relative to the starting of a set of drug candidates that are promising, and we can employ fully computational, expensive and accurate methods on them. This has been around for quite a while. What has happened and what is happening is that this traditional high throughput multi-stage virtual screening pipeline is being supplanted by AI-based methods. So each of these stages traditionally is computationally sophisticated, sometimes docking, sometimes HPC simulations, but now each of these stages is being supplemented by a AI-based surrogate AI-based method, which enhances the traditional simulation, traditional computation in different ways. What Impeccable is a pipeline that brings together this coupling of high performance computing based methods along with AI-based approaches to try to enhance the overall impact of such a drug discovery pipeline, and to obviously operate this at extreme scales in a way that a combination of scale and methodological advances is able to make meaningful scientific progress. And what we're really thinking of in this context is what's the system software both necessary to support these diverse methods as well as combined methods, but at the scale and at the sophistication needed to try to make real-time drug discovery. Okay, this is work that has been done as part of DOE's National Virtual Biotechnology Laboratory, an effort that came together very soon after the pandemic, the pandemic was declared. WHO declared this as a pandemic last year. And there are many different aspects to this project, but the project aspect that I'll speak to is namely the one in boldface, namely that supercomputing and artificial intelligence for design of targeted therapeutics. This being DOE, this project was primarily executed on DOE supercomputers, but it was also included and executed on NSF systems such as Frontera. So the idea was to bring these methods, scalable software systems, onto DOE's platforms and try to be able to make meaningful contributions to therapeutics, medical therapeutics. So the Impeccable pipeline, as kind of alluded to but looked at in a different way, is comprised of multiple stages of different computational methods. At the very start is the kind of staple of virtual screening, namely a large number of docking calculations. Docking is a kind of a cheap way of computing what a drug candidate might, how nicely it might bind to a drug, to a protein target. And one docking protocol is often not enough, so we employed an ensemble of docking protocols, but not just that. Along with the large number of ensemble docking runs, we created a docking surrogate to supplement the traditional docking runs. The second stage is what we call workflow 2, which is really using traditional molecular dynamics approaches to increase the sampling and therefore of various drug candidates in their binding to targets. But by using machine learned approaches, we're able to sample the space of configurations better. Long-winded way of saying that workflow 2 is a way of trying to understand both the energetics and the structural properties in a much faster way, so that there is additional scientific insight into understanding the binding of these drug candidates to the targets, which then are used to promote a more scientifically promising and engaging set of drug candidates to the next level, which is the set of binding free energy calculations, which, as mentioned earlier, are kind of the gold standards. Now, here the binding free energy calculations are many, not just one. We have a fine-grained and a coarse-grained. So in a way, you're starting to see how the impeccable pipeline is really taking this approach of multiple stages of different stages having different costs and accuracies and combining them together, number one. Number two, and at each of these stages, as you saw with workflow 1, surrogates for docking, workflow 2, machine learning driven HPC simulations, you have the coupling of machine learning with traditional computational approaches. Okay, so let me just try to set the scale so we can come back and then to the crux of the issues. How are we going to be able to do this on traditional clouds? So just to tell you what ensemble docking here involved, it involved really taking a library, in this case, a curated library of 6.25 million drug candidates, and binding them through docking calculations to 32 targets. So it's still the spike protein, but there are 32 different regions in the spike protein that had to be studied for possible therapeutic activity. Right? And what this previous slide is really showing you is two important things, is that on the left-hand side, the graph shows you that the same library, when docked against a large number of targets, has a lot of computational fluctuation. The time to solution varies by quite a bit. But the right-hand side figure shows you that the long tail distributions, that for any given target, the various ligands, the various drug candidates in that library take a very long time. So you start seeing the kind of load balancing challenges that you're going to get, in addition to the concurrency and parallelism challenges, namely you are trying to do as many docking calculations for a given target, but you also have many different targets at a given instant of time. And to try to reiterate the load balancing problem, here's what you see when you're running this on one of the supercomputers, in this case Frontera. You see that the docking rate that you get really varies over 2 to 4 orders, factors of 2 to 4 at a given instant of time. So really noisy and kind of reflecting the fact that you've got the long tail distributions, and you have to, that translates into a very interesting load balancing problem. Now, before going further, just try to say that a lot of this data is used to not just promote the right set of candidates to the next stage in the pipeline, but is used to actually train a surrogate. And lots of details here captured in the paper mentioned there. But the idea here is that if you can get the right surrogate trained, then for a given amount of computational cost at a given accuracy, you can span through the space of possibilities a factor of 10, if not 100 times faster. It's obviously a trade-off between accuracy and cost, but in this kind of space, you can, while preserving the accuracy, sample through 10 times more drug candidates using a machine learned surrogate. So that kind of tells you how impeccable starts doing things, not just at a big scale, but also faster than traditional approaches. And very quickly, just to talk about the second level of coupling between machine learning and traditional simulations, is a tool called DeepDriveMD, which supports machine learned driven ensembles of simulations where this coupling between the machine learning and the simulations is primarily in guiding the simulations into new parts of phase space, where the learned model is analyzing the trajectory data as things progress, as simulations progress, and determining the parts of phase space that have not been studied. So intelligently placing simulations into these new parts. And by doing so, the simulations progress by factors of 100 approximately faster than without actually steering the simulations. And this is just the graph at the bottom right-hand side is just one simple example when compared against a protein folding problem using vanilla simulations. Okay, so putting all of this together, and by skipping the last stage, I just want to convey to you the scale of operations of Impeccable, so that once we set the scale, we can then ask and compare what's happening on clouds today, given what's happening on DOE's infrastructure. So these numbers may not mean anything, but just to try to put this into context, the Impeccable project supported about 100 billion docking calculations, thousands of machine learning driven MD simulations, specifically about 10,000 plus binding free energy calculations, and about 2.5 million node hours over a range of supercomputers. At its peak, it used 8,000 nodes, which is approximately 440,000 cores on Frontera, and 4,000 nodes, which is a combination of approximately 24,000 GPUs and at least 200,000 plus CPUs at a given instant, or cores at any given instant of time. And all of this led to many important scientific insights, but this is just one example of a proposed antiviral drug for COVID. Okay, so there's the individual components that are important and then the overall performance of the pipeline, but it's also important to be able to couple these different stages together, because the ability to span this very large space of drug candidates is really possible only once you combine the different methods together. You can't, and I began by saying this, you can't just take any one method and just scale it, because the accuracy versus cost is simply not favorable for any one method. So what you really need is to integrate this, hence an integrated pipeline. And what the graph on the left-hand shows is the impact of coupling these different methods together. Lots of details here, but the upshot is that when you take integrated methods, you get lower, that's in black, values of binding free energies, and you can see lower is better compared to red when you just do this standalone. So integrated modeling is key in addition to advanced methods, in addition to scalable computing. And this is a challenge for many reasons. There's heterogeneity at every level and every dimension, as you can understand. And this is also challenging because, as I've shown you, there's a lot of computational variation in costs within a given method, the docking, the long tail that you'll remember, as well as the fact that you're now coupling simple function calls with very large, ambitious ensembles of simulations. So all put together, a very fluid mix of computation tasks. And the tables on the right-hand side show you that they can be, for the different stages, 1,000 factors difference in the throughput across different specific stages. And within any given stage, you can have quite a lot of variation in the cost of a given method. For example, the cost of a single docking candidate in what is the docking stage is about 10 million less than what would be the cost of a single drug candidate in the binding free energy stage. Okay, so what is the state of the art in cloud-based? So this is simply nothing that gets anywhere near this. There's a lot that has been done, and it would take several talks to cover the space, but using this one particular example of virtual flow as representing the state of the art in clouds, what I convey to you is that the sophistication of the methods, the integrated methods, the fact that you have these diverse types of methods put together has simply not been attempted on clouds. And what you have on clouds is a single stage, in this case docking, that has then been scaled to approximately 160,000 cores on Google Cloud. That's the largest that we have. We've been able to understand, at least in published literature. And in this case, whereas it's very important to be able to do these scalability tests, we don't know what the resource utilization is. We don't know what the overheads are. Nothing like the published data I showed you in the previous slides. Not to mention, and most importantly, that this is for one type of computation. And as I showed you, the value of impeccable and impeccable style, the high throughput virtual integrated pipelines is in the integration of different methods. So no idea how these cloud systems would work when you have the kind of heterogeneity that we discussed. So how we do it within the DOE system is using specialized system software, workflow tools, in this case, radical cyber tools. I won't get into the details, but these are now made available as part of ECP, Exascale Computing Project's ExaWorks software development kit, link there for you to look into. And just to give you a sense, you can now see that the throughput that we can sustain is about close to 150 million docking events per hour, highly non-trivial, while maintaining very high resource utilization, and while also supporting many of the downstream simulations concurrently. And what this really means is you need this very sophisticated system software that supports function calls on the one hand, Python function calls, but also MPI simulations at the other hand. And you've got to have all of this working under the hood at the same time. So hopefully in summary, drug discovery is complex and expensive. We've shown impeccable really does improve the enhanced effective performance. Scientific discovery requires the coupling of ML-based infrastructure with HPC infrastructure. And whether it be HPC or clouds, we have to rethink the system software in order to support these very advanced workloads, and we really need adaptive runtime systems. Thank you very much for your attention.
Okay, questions? I had a couple. So my first question is about your remarks at the end. When you were comparing the DOE with clouds, it wasn't clear to me whether that was a measure of the number of resources deployed or whether it was intrinsic to the architecture and capabilities of supercomputers versus clouds. Because in principle, clouds could be larger, could they not?
It could be. The question is what, so the answer, direct answer, I'm comparing both the number of resources that a single calculation, a single tool marshals for a single, if you will, workflow. The second thing I'm measuring and comparing is the scientific output. Let me start with the latter since that's easy. The scientific output of the largest published cloud calculation is 50 million docking events an hour. Compare that to ours, 150 million per hour, factor of 3, factor of 4 more, sustained over many, many more hours. Their 50 million is their peak. So they do 1 billion in about a day. We do 1 billion in under 12 hours. So that's the head-to-head scientific. So if you have 100 billion drug candidates to study, then the largest published
Yeah, but that's not quite my
cloud
whether that was due to
done by people.
Continue.
Right. And I'm coming to what, so the specific Nature publication by the Google team use 160,000 cores concurrently. Now, I'm sure there's more cores in the cloud, without a doubt. The question is, how many cores are concurrently utilized in a single workflow? And that is capped for throughput screening at 160,000. Whereas, as I mentioned on DOE Summit or Frontera, there's 400,000 cores. So I think the point is, how many have been marshaled concurrently for a single application? That is not where Cloud's forte is. Cloud's forte is in many, many distinct transactional instances. I hope I've answered your question, Jeffrey.
Well, not really. Namely, you mentioned all the heterogeneity and things like that. So naively, clouds might be preferable because the efficiency of operation is quite good for random asynchronous things going on. Whereas your DOE supercomputer, you really have all your nodes, you better make them all run together in an efficient fashion. Whereas clouds can be efficient even if you don't quite do that as well. And there's sort of a difference between a grid of resources without strong synchronization and the total computation, because I think your problem is a lot of modest computations, which add up to a total giant computation.
Very important details there, Jeffrey. You are right. The DOE work takes the full end stage pipeline with the docking at the top and very expensive MPI simulations at the bottom. There is no equivalent published end-to-end pipeline for cloud. So in that sense, it is just a single layer, the docking layer that I'm comparing. And that might be unfair, but I think that's there's a broad distribution of runtimes in that layer as well. So it is about managing a broad load balancing, a broad distribution of docking events computations. To give you a sense, these vary from seconds to several minutes. So that's the distribution of each computational event. We're not talking about millisecond, microsecond, we're talking about many seconds or the tens of seconds to several minutes.
Well, here's my second question. You gave a little talk recently where you discussed Rosetta Fold and AlphaFold 2. How does that fit into this discussion?
Most of the work done with Rosetta Fold and AlphaFold are for protein structure predictions, and they're all offline in the sense that millions and millions of dollars worth of computing is used to train the models, but AlphaFold, so on and so forth. But once trained, they're used in offline mode. Clearly, it's valuable to try to bring those trained models into our integrated pipeline. And we have a project within the DOE system where we're trying to bring AlphaFold, Rosetta Fold as one of the, if you will, stages into the impeccable pipeline. That's one important difference, but I think the problem space is slightly different. Once AlphaFold and Rosetta Fold are not about the fold of the protein when bound, when a drug candidate is bound, but when it is in its native state. So the holy grail is to find for a given protein sequence, what's the native state? There is absolutely zero work done in AlphaFold and Rosetta Fold of finding the folded structure when a drug compound is bound to the structure. And obviously that's somewhat the next level. I'm sure they're working on it, but that's where some of the getting both the structure, but also the energetics is going to be so important. Long-winded way of saying that the training that they've done so far has just been on data without any physical significance. In order to get the fold right when they have drug candidates embedded, they are going to have to do the energetics, and that's the kind of simulations we're doing. The energetics comes from molecular dynamics, and they don't use molecular dynamics up to this point.
So the work to say, I think you mentioned Austin Clyde was doing the surrogates that you mentioned. So that's different from Rosetta Fold surrogates.
Yes, so that surrogate that we're doing with Rick Stevens' group, that is just for a surrogate for the docking, right? And there you're not predicting the structure, you're just predicting the most likely goodness of fit of a drug candidate to a protein, assuming a fixed protein structure.
Well, somebody else should ask a question. I've monopolized it.
This has been a great discussion, actually, especially this latter between you and Shantenu. Unfortunately, we're out of time, and so I've got to get ready to go to the next section. So I'll say goodbye.
Bye, Dennis. Happy to field questions offline, and thank you for the opportunity to present.
That was really great. It was great.
Thank you. All right, so maybe we should take the hint and say goodbye and thank you to everybody. And we will, hopefully this recording has worked and we will put it online as they claim in less than a day. Thank you very much, everybody.
Thank you all. Great talks and great discussions.
Thank you all. Bye.
Well, bye-bye.
Bye.
Bye.